So let's start with question 3.5, where x is integrable random variable. Then you have to show that limit x goes to infinity, probability x greater than x into x goes to 0. So we'll only show it for non-negative random variables first, and then we'll extend it further for other random variables. So x is greater than or equal to 0, we'll show the result. Let's take the lower direct approximation of x, which gives us this result, which is expectation of the lower direct approximation is equal to this number. And we start from k is equal to 0 because we don't need any number of the sort where k by 2 to the power is negative because x is greater than or equal to 0. So next inequality is very crucial, which shows that expectation of the lower direct approximation is greater than or equal to when you start from k is equal to I to infinity, where I is some natural number bigger than 0. So instead of starting from 0, we can start it from some other I, and definitely the answer in case of 0 will be bigger because all of them are positive terms. And the second to third inequality is obvious because k by 2 to the power n that increases. So instead of doing k by 2 to the power n every time, if we do I by 2 to the power n, so that result will be lesser than when you do by k by 2 to the power n. That gives us I by 2 to the power n outside. I by 2 to the power n summation probability x n lower is equal to k by 2 to the power n from I to infinity, and that is nothing but equal to probability of the sum here. The sum here basically is nothing but probability the lower direct approximation being greater than I by 2 to the power n. So I by 2 to the power n divided probability the lower direct approximation greater than I by 2 to the power n. So now we go for the most important key step. So for any x which is in R plus, basically which is non-negative. So x times probability x greater than or equal to x can be written as xn bar plus 1 by 2 to the power n. Instead of x, we can write xn bar plus 2 to the power n. Again, small xn bar is the lower direct approximation of the number small xn. The probability x greater than or equal to x. Again, this second term can be replaced by probability lower direct approximation greater than lower direct approximation of xn minus 1 by 2. Again, why? Because if x is not equal to xn lower, then again xw will be greater than or equal to x, which implies xn bar w will be basically omega will be greater than or equal to xn bar. But if x is equal to xn, then in that case xn lower bar will be xn small xn lower bar minus 1 by 2 to the power n. But in either cases, we can show that if x of omega is greater than x, then xn bar of omega is greater than xn small xn bar minus 1 by 2 to the power n. So we can write x into probability capital X greater than or equal to x is less than or equal to xn, which is the lower direct approximation of the number small x plus 1 by 2 to the power n into probability of uh, random variable xn, the lower direct random variable greater than or equal to small xn minus 1 by 2 to the power n. And then again we can rearrange it as small xn minus 1 by 2 to the power n plus 1 by 2 to the power n minus 1, which is 2 times 2 to the power 2 by 2 by 2 to the power n, which gives us 1 by 2 to the power n minus 1 into probability. So it's basic manipulation which gives us the result. So now the key step is, since expectation of x is less than infinity, expectation of xn is also less than infinity, because basically we can get expectation of xn is less than m for all there's some n which bounds the expectations of all the direct approximations. So now 1 by 2 to the power, we can find some n big enough such that for a given epsilon. So let's fix an epsilon. So for a given epsilon, we can find n big enough that 1 by 2 to the power n minus 1 is less than epsilon by 2. This can be done as n goes to infinity. And also for that particular n, since expectation of xn bar is less than m, we can find, since the tail of the expectation has to go to infinity because it's a series and the series is finite, so the tail goes to infinity. So we can find some I basically from where the tail goes to infinity. So which gives this result that there must be some I from which summation I to infinity k by 2 to the power n probability xn bar is equal to k by 2 to the power n must be less than epsilon by 2. This summation from here. Again, as we've shown earlier, this summation is always this summation. This summation is always greater than I by 2 to the power n probability xn bar is greater than or equal to I by 2 to the power n. So here again that will show that I by 2 to the power n xn bar is greater than I by 2 to the power n is less than epsilon by 2. So now if we take, so for all x in R plus, which have this property, the lower direct approximation of a particular x with respect to that particular n minus 1 by 2 to the power n is equal to I by 2 to the power n. It must be some I by 2 to the power n again for the given I. And for those x, we can write x times probability capital X is greater than or equal to x is less than this inequality which we've shown previously. And this is less than I by 2 to the power n plus 1 by 2 to the power n plus n minus 1 into this probability. So the second term, so this term is less than epsilon by 2 because this second term again is less than or equal to 1 because it's the probability of a number. And the first term, as you've shown by the tail, converging tail of the probability distribution, sorry, the converging tail of the expectation, we can also show that this term is less than epsilon. So epsilon by 2. So again, so for all x which have this property, we can show that x probability x is greater than equal to x is less than epsilon. So now we have only shown for those x's such that lower direct approximation of the small x is equal to I plus 1 by 2 to the power n basically. So all the x's in this interval basically. So if the x is greater than this interval, then in that case we can write this generic result for it, which is equal to this. This breaks up in two parts. The second part is again less than epsilon by 2 because the second part is only dominated by 1 by 2 to the power n minus 1, and that was like the n was chosen, so it is less than epsilon by 2. And in this particular case, when x is greater than I plus 2 by 2 to the power n basically out of this interval, in this particular case, because we have chosen I in such a way that summation I to infinity k by 2 to the power n probability lower diagonal approximation is equal to k by 2 to the power is less than epsilon by 2. So x is greater than I plus 2 by 2 to the power n, which means that xn, uh, lower bar minus 1 by 2 to the power n is greater than I by 2 to the power n, which shows that the second term also less must be less than epsilon by 2, which is shown in this arithmetic clearly. This arithmetic relies on the fact that if you, since xn bar, small xn bar minus 1 by 2 to the power n is greater than I by 2 to the power n, so if we take this time, this is less than this summation, and this summation starts from xn bar minus 1 by 2 to the power n, and again that summation must be less than equal to when it starts from I, because this number is smaller than this number is greater than I, so we're adding more terms in the second term, and that again is always less than epsilon by 2 is chosen earlier. So we've shown that for all x, we have shown that for all x which are greater than I plus 1 by 2 to the power n, I plus 1 by 2 to the power n, all x greater than I plus 1 by 2 to the power n, x times probability capital X greater than equal to x is less than equal to epsilon. So we have cumulatively shown that for all x in this interval, x times probability capital X is greater than equal to x is less than epsilon. So this ni pair depends on epsilon here. So now we can go for the general result. So given epsilon, we can find a j, and j is basically n plus I plus 1 divided by 2 to the power n. So that for all x in j to infinity, we have this result: 0 is greater than equal to, this is again 0 has to be less than equal to this number, because this number is totally positive, but this number is less than equal to epsilon, which means that this number must go to 0 as x goes to infinity by the definition of limits. Also, now for the general random variable, integrable random variable, expectation of x is defined, which means that expectation of mod x is defined. So now, since mod x is a non-negative random variable, the same techniques as shown above can work for mod x, and we are done, because mod x is a non-negative random variable, and we are just supposed to show it for mod x, and we already shown the technique for non-negative random variable generally. So we are done. The only key step here was for an integrable random variable, the expectation of mod x is also finite. That is it. So again, now let's go to question number 3.9, the second question. Find the exponential of, find the FGF of exponential lambda, which is lambda by lambda minus theta, for theta between 0 and lambda. Lambda non-inclusive. So the only important fact here is that since it's exponential, we have a PDF, a good PDF, and we just have to find the expectation of e to the power theta x. The only key thing here is this integral is only valid if theta minus lambda is less than 0. So theta minus lambda has to be less than 0, basically theta has to be less than lambda. So yeah, that's a typo here. It's theta should be less than lambda, not lambda less than theta. So theta is less than lambda. So basically, in particular, 0 greater than theta less than lambda. So in that particular case, we can get the expectation by some clear integration techniques, and the expectation comes out to be lambda divided by lambda minus theta. So this is very general. Only key fact here to be noted was the integral is valid only if theta minus lambda is negative, which means that theta should be strictly less than lambda, and in particular theta has to be between 0 and lambda, lambda not inclusive. So we're done with this, and thank you.